Hi everyone, my name is Rutvik Choudhary, and today I will be presenting our work Speculative Privacy Tracking, or SPT for short. It's a way of leaking information from speculative execution without compromising privacy. My co-authors are Jiyong, my advisor Fletcher, and Adam Morrison. The goal of speculative execution attacks is to leak secret information beyond what the non-speculative semantics of the program allow. An attacker will do this by taking advantage of speculation, an essential feature of high-performance modern processors. Let's take a look at the simple case of variant 1 of the famous Spectre attacks. Suppose we have the following code where X is used to perform an indirect access on array 2. A bounds check theoretically prevents the program from reading data beyond the arrays. However, an attacker can use speculation to trick the processor into doing just that. The first steps the attacker performs is to control the input and mistrain the branch predictor. After that, the CPU will use the mistrained predictor to speculate past the bounds check. In general, we usually abstract away the predicate since the exact expression is unimportant. We only care that it introduces speculation. Now this attacker-controlled value of X is used to load some value of interest Y from memory. This is known as accessing a secret, and we abstract it away as a primitive. The next step is that Y is used to index into array 2. Eventually, the branch will resolve false and all instructions in the if body will be squashed. This will leave no architectural trace. However, the access to array 2 will leave a microarchitectural trace in the cache. The attacker can use this to determine the value of Y. We abstract this away as Y being an operand to a transmitter. A transmitter is simply any instruction with operand-dependent hardware resource usage. All speculative execution attacks essentially consist of an attacker taking data from an accessor and passing it to a speculative transmitter. What makes these attacks so hard to prevent as a programmer is that while it's easy to reason about the non-speculative behavior of a program, it's much more difficult to reason about what exactly might happen to your code under speculation. And so, code you thought was safe might actually be vulnerable. Spectre Variant 1 is a type of speculative execution attack where both the accessor and transmitter are speculative. Fortunately, this is a well-studied form of the problem. To thwart an attack, we need to prevent the data returned by a speculative accessor from reaching a speculative transmitter. A naive scheme would simply wait for the transmitter to resolve as non-speculative before executing it. But this has extremely high overheads. Prior works STT and Specule instead make the observation that since they're only concerned with protecting speculative accessors, they can treat the result of non-speculative accessors as public. If we see a speculative transmitter that only has public operands, then we don't need to wait for it to resolve non-speculative. We can just go ahead and execute it. This results in reasonably low overheads. Unfortunately, this only solves half the problem. It's also possible for the accessor to be non-speculative. In our example, we could do this by moving the accessor to be outside of the if body. Now the data being leaked is part of the architectural state of the program. As a result, SPT would not protect this data at all. Protecting non-speculatively accessed data is important for security-critical applications. For instance, constant-time programs. These are programs that have been specially written so as to not pass sensitive data to transmitters. Essentially, even if two runs of a constant-time program handle different secret values, their observable behavior should remain identical. Unfortunately, it has been shown that constant-time programs are vulnerable to speculative execution attacks. For example, consider a simple transmitter that leaks X. Under the non-speculative program semantics, the transmitter would never execute if X contained some secret data. But an attacker could abuse speculation to make the transmitter execute while X contains a non-speculative secret. To maintain the security of constant-time programs, we need a scheme that can thwart attacks like this in an efficient manner. Again, the main idea is that we need to stop sensitive data flowing from an accessor to a speculative transmitter. But how can the hardware identify truly sensitive data? The hardware could conservatively protect the result of all non-speculative accessors. However, if we do this, we're going back to the naive scheme, which is waiting for transmitters to resolve non-speculative. The problem with this is that not all data is sensitive, and so we're being extremely overprotective and will incur high overheads. Alternatively, we could have the software mark exactly what should be protected. This definitely would be the most precise solution, but this requires software and ISA level changes, and so code would need to be rewritten and recompiled. The conservative method had the advantage of being completely transparent to the programmer. At first glance, it seems like we'll have to choose between software transparency and precision. However, we've come up with a new framework that actually allows us to get the best of both worlds. To solve the problem of speculative leakage of non-speculatively accessed data, we propose our framework Speculative Privacy Tracking, or SPT. This is purely in hardware and requires no software or ISA changes. We will detail SPT's implementation in the following way. We first identify what we mean by a secret. Then we go over the manner in which we protect these secrets in hardware. Next, we talk about how we manage to disable protection for data that is dynamically inferred to be not a secret. After that, we discuss how to extend our ideas to encompass information flow beyond just that between registers. Finally, we will explain all the modifications we need to make to a baseline processor to implement our framework. So without further ado, let's begin. Our first big idea is that any data that leaks during the program's non-speculative execution does not need to be protected during the program's speculative execution. The intuition is that we don't need to bother protecting what the program inherently leaks even without speculation. We're essentially defining a secret as any data that does not leak in a non-speculative execution. From this, we get a nice security property. Any data that the program protects from leaking in a non-speculative execution is guaranteed to not leak in a speculative execution. Recall that programmers writing constant time code already take care to not pass any sensitive data to non-speculative transmitters. So under our framework, they're protected from speculative execution attacks with no extra thought or effort on their part. But now how can the hardware deduce what is secret in a software transparent way? The key idea is that the hardware already knows when transmitters resolve as non-speculative, and it's precisely the operands of these transmitters that are leaked non-speculatively. Thus, we can track secrets by using taint tracking in the following way. We assume all newly accessed data is secret initially. We do this by marking it as tainted. When we see a transmitter retire, we mark the operands as public or untaint them. We can protect secret, aka tainted data, with a simple policy. If a transmitter is speculative and it has tainted operands, it's prevented from executing. Dynamic information flow tracking in the hardware propagates taint through the data flow graph. This is required in order to know what other data to enable protection for. We can take it a step further though and use the same idea of dynamic information flow tracking to know what other data we can disable protection for. When a value becomes untainted, we use the set of currently untainted values along with any public information to compute what other values the attacker knows, and we add these new values to the set of untainted values. Essentially, this is propagating untaint through the data flow graph. Prior work has already discussed propagating untaint forwards through the data flow graph. Our insight is that we can do it backwards as well. To untaint in the forward direction, we can piggyback off the well-known idea of forward information flow. Suppose we have some operation in the data flow graph that takes two inputs and produces an output value. Let's further suppose that this operation is deterministic such that the same inputs always yield the same output. In that case, if the attacker learns the inputs, then they can deduce the output by computing the operation themselves. Thus, if the input is untainted, then we can untaint the output. This is propagating untaint forwards through the data flow graph. It's possible to propagate untaint backwards as well. Consider the case of a simple move operation. All this does is take an input register and copy its value to an output register. We know that whenever the attacker learns the output, they trivially learn the input. Thus, whenever the output is untainted, the input can be untainted as well. Let's consider the more complex case of an addition between two inputs. If the attacker knows the output and one of the inputs, then they can determine the other input using some basic algebra. Thus, if the output and one of the inputs is untainted, then we can untaint the other input. Untamed propagation is a neat idea, but we need to be careful when applying it. We've shown that we can use the data flow of the program to deduce what is non-secret. For this to make sense, we of course have to assume that the program, aka the static data flow graph, is public. However, what if the dynamic data flow graph, also known as the set of in-flight instructions, is a secret? This can happen if the program counter or branch predictor state depend on secret data. In that case, the attacker could learn something by observing untaints, or worse, they could coerce an untaint to occur when it shouldn't. We can get around this problem by taking a page out of STT's book. Specifically, we can borrow STT's mechanisms for ensuring that the PC is independent of any tainted data. Even though we've expanded the definition of tainted data to include both speculatively and non-speculatively accessed data, the mechanisms described in STT can still work. This guarantees that the execution graph of the program is never a function of secret data, and so we're free to propagate untaint through the data flow graph to our heart's content. Now that we've dotted our I's and crossed our T's, let's take a minute to see how all these concepts fit together. Let's walk through a simple yet comprehensive example. The instructions are listed in dynamic order. Based on the context of the example, we denote I1 as an accessor and I3 and I6 as transmitters. However, note that all loads are both accessors and transmitters since they not only return secret data, but also leak their address via a cache side channel. The first thing that happens is that R0, R3, and R5 are all tainted since they are the result of accessors. After that, the taint is propagated through the dataflow graph. The rule is simply that the destination of an instruction is tainted if any of its sources are tainted. We see that transmitters I3 and I5 now have tainted operands and so are blocked. If we look at the current state of the program, we see a relatively bleak picture where all transmitters are blocked. However, one domino falling will now topple the whole chain. Suppose that I3 resolves non-speculative. It can then be unblocked and we can untaint its operand R1 as well. Now that R1 is untainted, we can propagate this untaint backwards through I2 by using the rule for add. Remember that program constants are by default untainted since we assumed that the program is public. Note that R0 is part of two separate data flows to two separate transmits. So when we untaint it in one branch, it affects the other branch as well. This is like a lateral untainting. What happens next is that R4 is untainted via forward untainting through I4. Looking at I6, we see that it no longer has tainted operands. Therefore, the transmitter is free to go even though it's still speculative. This example shows the true synergy between our two big ideas. Untainting the operands of transmitters that have resolved non-speculative is the initial spark, and untamed propagation is the fire that spreads afterwards. While this is a cool example, it's only one side of the data flow coin. Our scheme as is only tracks taint at the physical register level, and the data returned by accessors is tainted by default. Essentially what we're doing is we're drawing a line between the core and the architectural monolith of memory. We only track taint above this line. Data coming in from below is always tainted. This keeps the mechanism simple. However, the problem is that data sent down below the line is re-tainted. This can undo some of the benefits that we get from untainting. Consider the following x86 assembly snippet. We assume that k is some public constant and so is untainted. We put the constant on the stack and pass its address to the function foo. Then once inside foo, we get the value back off the stack into a register for local computation. At a high level, we know that k should remain untainted since all we did was pass it to a function. However, since it went through the stack, it re-emerges as tainted. The strawman solution would be to move the line all the way down and track taint through all of memory, but that's far too expensive. Fortunately, the microarchitectural implementation of memory consists of a cache hierarchy. Thus, we can move the line part of the way down to just below the L1. That is to say, we can track taint for data in the L1. This way, only accessors that miss in the L1 will return tainted by default data. Higher level caches typically have high hit rates, and so most untainted data written to memory will remain untainted when read back. This is the last of our hardware mechanisms of interest, and so now we can see how everything comes together. We'll start with a classic out-of-order processor as a baseline, and one by one we'll add the needed modifications to arrive at our full SPT design. For the sake of simplicity, only relevant hardware structures will be depicted. The first modification we make is to add taint status bits to the register alias table, the reservation stations, and the load store queue. We keep the taint status bits distributed like this, rather than centralized in the physical register file, in order to prevent bottlenecks from accessing them. The next thing we need to do is to add something that will tell us when instructions have resolved non-speculative. For this, we again adopt logic from STT. STT refers to the point at which instructions resolve as non-speculative as the visibility point, or VP. It has logic designed to detect when instructions reach the VP. We can use it and broadcast this result out to relevant structures so that they can untaint as needed. We also need to augment the reservation station with logic to perform forward and backward untainting. This happens in parallel for each reservation station entry, and we can broadcast any new untaints to other structures in the processor as well as to other reservation station entries so that they can propagate the untaint further. Finally, we add what we call the shadow L1 to the data path. This is a structure that stores the taint status of the L1 data cache lines at a byte granularity. It's accessed in parallel with the L1 data cache, and it can piggyback off the logic used to determine cache hits and cache misses, as well as to handle eviction of cache lines. We should note that we also need to add some more logic to the load store queue to handle store to load forwarding in a sound manner. We've omitted these details from the talk for the sake of time, but they can be found in the paper. We've taken these changes and we've added them to the Gem 5 simulator in order to evaluate their effectiveness. The results are quite telling. We evaluated our framework under two threat models, Futuristic and Spectre. The Futuristic model lets the attacker exploit all forms of speculation, while the Spectre threat model assumes that the attacker only exploits control flow speculation. We evaluated our modified processor on the Spec 2017 benchmarks, and we show the averages here. We first evaluated what we call a secure baseline. This is the naive scheme where we delay transmitters until they resolve non-speculative. We can compare it to a processor that 1. Untaints the operand of transmitters that resolve non-speculative, and 2. Propagates this untaint forward. Note that this scheme achieves much lower overheads than the secure baseline while achieving the same protection scope. We then added the novel backward untainting to the processor and saw that it cuts the overhead by about 2 percentage points in the Futuristic model and 4 percentage points in the Spectre model. Including the shadow L1 on top of that further cuts the overhead by 5 percentage points in the Futuristic model and 3.5 percentage points in the Spectre model. The full SPT design consists of all these additions combined, and we see that it does extremely well compared to the secure baseline. It reduces the overhead by a factor of 3.6 in the Futuristic model and a factor of 3 in the Spectre model. Furthermore, while SPT adds overhead on top of STT, it's a reasonable amount considering that it greatly expands its protection scope. Specifically, we mentioned that STT is insufficient to protect security critical code such as constant time programs. If we look at our full SPT design applied to some constant time programs, we see that we once again significantly reduce the overhead of the secure baseline. Thus, SPT can not only protect constant time code from speculative execution attacks, it can do so in a transparent and efficient manner. To sum everything up, our main contributions are: 1. We developed a way to identify secrets that is both precise and software transparent. Any data that is leaked in a non-speculative execution is not secret and thus safe to leak in a speculative execution. 2. We achieve a meaningful security guarantee that is well motivated by today's security critical code, such as constant time programs. Namely, if the program already prevents non-speculative leakage of data, then that data is guaranteed to be protected from speculative leakage. 3. We detailed how to propagate non-secrecy in a sound manner. We use forward untainting and the novel backward untainting to selectively disable protection on data that we can prove can be inferred by an attacker over non-speculative covert channels and any public knowledge. 4. We implemented our scheme in hardware and showed that it achieves well-reduced overheads compared to a naive but secure baseline. Thank you for coming to our talk.